Hello, I'm Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video, as you can see here, is going to take a look at the call time stack, how to access it, how to use it, at least start out doing this, push and pop operations, and creating functions. We've been using the Irvine library, but now here's a chance to start creating our own custom functions. So before we think of the call time stack, we can fall back on the actual stack data type. It's similar, but it's not necessarily the same exact thing as what we're going to be talking about the rest of this lecture. So say, what is a stack? I like to think of it as a very fragile stack of dinner plates. So there you go, that's a Shutterstock original there. You can only add to the top of the stack when it comes to the data type, because if I tried to grab any of the other plates underneath, since they're very fragile, they would break. So I'm not allowed to access them or see what's on them or see anything about them. I can only look at what's on the top. And so, yeah, so if I'm trying to remove or look at anything but the top plate, everything will break just because the force of gravity pulls everything down and just the way physics just cracks, fragile things. So when we call anything that's in addition to the stack, we call that a push. Just think, if you're a C++ person, think to when we taught advanced C++, how there's push back and push front and this and that and everything else. That's very similar terminology. And the same goes if there's a push, then there's a pop. So you push to put something on, you pop to take something off. And generally speaking, there's a completely separate functionality involved when it comes to seeing the top element. And for various reasons, they're not the same thing, where you have to do things one at a time. You have to do both operations if you want to actually see the top of the stack and then remove the top of the stack at the same time. So at this point, since it doesn't matter what language, Java or C++, if you're one of my students, you are supposed to have already been through this sort of understanding of stacks and queues and priority queues and all the other data structures that come with the different various programming languages. So at this point, you'll need to fall back on that information. There's nothing here for me to continue on discussing. And now we're ready to discuss, so here's the stack data type, last in, first out, as we're discussing, because as I'm putting things on, it's stacking up. And so it's, so whatever's at the top is the last thing that was put on. Whatever's at the bottom was the first thing that was put on the list, or the stack. And so again, gravity and static forces would play a role with a real-life stack of information. And of course, physical computing is not the same type of deal. The limiting reagent, instead of gravity, like toppling over if we had a ton of plates, or just everything breaking from the weight of all the plates, we have the physical limitations of how much RAM our computer has, and basically how much stack space we have set aside for the stack in our program. So as we're saying here, the runtime stack is similar, but we have more access to the data sitting on the runtime stack than we do in the stack data type. And when we get to chapter 8 stuff, when we get to EBPs and ESPs and all sorts of stuff, you will see that we can go crazy and we can pretty much access anything we want in that stack, but the stack is wound and unwound in such a way so that when the functions come and go and all the local variables come and go and the parameters come and go, the stack just magically can handle that and everything just works out perfectly fine. So the runtime stack is managed throughout, so here's the ESP and EBP. The Esp register is maintained automatically whenever, you'll see here in a couple slides, when we talk about the push operation and the pop. Esp, that's why I haven't discussed it, because I haven't wanted you to accidentally blow this thing out and use this and get used to using it and then have me tell me, nope, you can't do this. Esp is maintained automatically as you push and pop information, and the stack is also maintained as well. So there's a code segment, that's where all the physical binary of all the operations that your program is going to perform, that's where that is stored. You have the data segment, which stores all your global variables for your program, and now you have your stack segment. Again, we do not directly tinker with the stack segment, it just It's just part of what the program allows, so we don't have to worry for that, but just understand that that is the third segment here. So we're not going to deal with EBP in these lectures. That is, again, a Chapter 8 thing. And we're not going to be directly using ESP, just like we don't directly work with the flags, the status flags, when we're discussing all the operations that affect the status flags. So for right now, the ESP register we will indirectly be using by using push and pop operations. And so let's see. So the one thing you have to understand when it comes to the way the stack works is we think of a stack of plates, like, because of the way gravity pulls everything down, that the stack works its way upwards. But in a computer program, the stack works the complete opposite, and it's an anti-gravity, however you want to think of it. And so this is going to play a huge role in Chapter 8 later on, in later lectures. So the runtime stack, every time I push information onto it, the stack actually works its way downwards. So just think of a mirror image photo, or just think of something where, anti-gravity is actually putting the bottom of the stack at the top. So all the memory addresses here, 1000 hex, FFFC, you can see as I work my way down that the numbers are getting smaller and working their way towards 0. So that's a big deal. Not right now again, but it will be a big deal later on. So if you get it in your head now, you'll have it in your head later as well. So the ESP register will always point to the data element at the very top of the stack. So like right here, like the 6 is on the stack right now. That is where ESP is pointing. If I push information onto it, ESP will move along with the new data. And if I pop information off, ESP will move accordingly as well to get rid of the data that is was currently at the top of the stack. Every time we push something onto the stack, two things need to occur, as I was just describing. The information actually needs to go onto the stack, but it needs to also go onto the stack in a place where it doesn't overwrite anything else. So a few other little odds and ends. Every time we push information onto the stack, we are going to be pushing 4 bytes of information. Even if we have a byte or a word, we need to find a way to convert that into a double word as we push that onto the stack. So keep that in mind. And so the first thing that happens, right, is that the ESP register gets moved 4 bytes down. So basically subtracting 4 bytes from the current ESP pointer, and then the data goes in. So like after this, what is this, 165? That goes onto the stack after the 6. ESP moves down, 165 gets put into that spot. And so what would happen if the order of operations were reversed? If I put the information in first, then move the stack, well then basically you would lose at least one piece of information in the process, because you think of it this way, the 6 would be blown out by A5 and ESP would point 1 past the last element that is inside of this data structure. And so here we go. We've been pushing some stuff along here. So here's the same stack after pushing more information onto it. Again, ESP points to the top of the stack, and the stack is growing downward. I'm saying all these things again, just for repetition's sake, just so committed to memory. So there, I put a 1 on the stack, then a 2, and so the stack can overflow. That's what a whole website where a lot of you guys get some information from when it comes to this class and others, and so do I when I need help with things as well. But the stack can overflow, but it usually takes a lot of effort. And sometimes it doesn't take a lot of effort at all, and sometimes you have to push, and next thing you know, you're crashing your computer. So again, a stack overflow is not the same thing as an infinite loop, because an infinite loop is something that never ends. A stack overflow is something where you keep pushing information onto the stack to the point where you have no more space remaining and the program actually crashes because it's not going to blow out something else because you've run out of memory. And what is the stack but RAM? And so you've overflowed the RAM that you were given by the operating system when your program was running. So then at a high level, if I can push information onto the stack, well then I can obviously pop information off of the stack. So the first thing that happens is whatever ESP is pointing at is copied somewhere, either to a register or to RAM, to a variable somewhere, in your program. And so then the ESP register is reduced by, added by 4. 4 is added to the result, because I'm now working my way back upwards. And so the data previously at the top of the stack will be blown out the next time we push onto it. This is where I get into a lot of discussions with students whose programs work exactly one time, and then they're like, well, it works. And what happens is if I ran this a second or third or fourth time, either you'll crash the computer, you will definitely not get the correct results, and so forth and so on, is because you'll be accessing stuff that doesn't really belong, because once I push this information off the stack, it really doesn't make any sense to blow out the value, because the stack is pointing to the top of the stack, the current top of the stack. Whatever's in there is considered garbage. That's why we'll see in Chapter 8, and we'll think about it when you think about the way C++ and Java works. When a local variable is taken out of scope, what is happening is just this ESP, the pointer on the stack, is being removed. And that's why when you close out, you have a for loop or something with an I, int I equals 1 to 10 or something like that. You hit that closing curly brace, you can't use I anymore. And that's because the stack is unwinding, because you don't need that information anymore, and the stack is unwound because you're not using that variable. And so at any time, anything else can come in and clobber that thing out of existence. So because of that, the programming language, the compiler, tells you, nope, you cannot access that. If you wanted that variable to be in scope, find a different way to make it happen. Take the int I out of the for loop and bring it in front of the for loop so that it's accessible when the for loop completes, and so forth and so on. So the big deal here is the information's still there, and sometimes, again, students do access it accidentally without meaning to, but the whole thing is if I went in and changed a little bit under the hood, your program doesn't work anymore. And so there's a challenge there, right? Because your program to you works perfectly, but it does not work perfectly, and so there has to be deduction in points for something like that. Okay, so here is how we do push and pop. I mean, if you could pretty much imagine how things work out here. This is how you use push and pop in the x86 assembly language. So we only have a few registers on which a computer can do all the work, and until Chapter 8 comes around, we're going to be fighting, right? EAX is the accumulator. ECX is for loops. Again, EAX and EDX is for multiplication and division. ESI, EDI, and I just showed you that even though ESP and EBP exist, we don't touch those because the stack is maintained automatically, and if we ruin that, we blow the stack out and nothing's going to work for us. So, goodness gracious, right? We have to manage that complexity, and so sometimes we have to kind of push information and pop it back later because there's just not enough space for all the things we have to do. So for something like this, calling a specific function, I push ESI, I push ECX, I push EBX before I modify it. Because these things, according to this dump mem function, part of the Irvine library, these registers need to be modified to be able to work the function correctly. And so obviously these registers, like any other variable, can only hold one value at a time. And so if I blow them out, I can't get them back. So if I push them onto the stack, then change them up and use them and put them back, then it's like nothing ever happened. And so remember, this is a stack here. So if I push ESI, then I push ECX, then I push EBX, see how it's all listed out here, I have to make sure that on the back end of this, when I pop everything, put everything back to where it was, I do it in the reverse order. So if I'm pushing it in this order, I have to pop it because the first thing on has to be the last thing off. And so again, you don't always have to do this. This isn't if you didn't care what ESI, ECX, or EBX are before you do this, then you don't have to push and pop this stuff. But for nested loops and things like that, where you need to use ECX, but only ECX can be used when you hit a loop, but I want to have a doubly or a triply nested loop, I'm going to have a stack. Or I can use variables to maintain this information, but the easier way is to use the pushes and the pops of the stack. And again, one more time here, make sure, I see this all the time, make sure you push and pop things back, because it's a stack in reverse order. Because if you put things back, it's one of those, if you put them back in the wrong places, you did 80% of the work, but that 20% will kill you, because I'm expecting the variables to be put back to exactly their values and not somebody else's swapped values. So be very careful when you do this kind of stuff. Okay, so as I was saying here, like pushes and pops for, here's a doubly nested loop. And so, the loop instruction is reached. It only cares about what's in ECX, as we've shown in previous lectures. And so if we're trying to maintain two separate loops, we have two competing interests for this ECX register, right? And so we have to make sure when we hit the loop statement, we hit the correct value of ECX for the correct loop. So you notice obviously you notice here in bold font, you see the push and the pop. And so what is happening here is the outer loop out here is maintaining 100. And I set this up to be easier for us doing the countdowns. We don't normally do the countdowns, but we're going to do it here. And so we're saying ECX is set to 100. And then is part of, we're initializing it here, but then I'm pushing it. When the first thing I do when I get into the actual start of the outer loop is to push that information onto the stack, because I need to do the inner loop, right? You see this is the inner loop right here. And so I'm setting it to 20 right after, but I've maintained the 100, right? So everything is good so far. And then you don't mind everything else. I loop inner, I loop inner, I loop inner. This 20 is counting down, 19, 18, 17, 5, 4, 6, 3, 2, 1. And when it hits 0 and it falls through, the loop is complete. I've done 20 iterations of this print statement. And then what will happen now that I fall through is ECX is 0 when it comes out, but I pop the information back, so now it's 100. And then I decrement it when I hit the loop. And so 100 becomes 99. I come all the way back up, and then I push the 99 onto the stack. And I do it again 20 times. And then I reduce it one time when I hit this loop, when I pop back and everything. And you can see where this is going now. This is exactly how you can go about doing a doubly nested loop. So this will count down 100 times, 20 times over. It'll actually print out 2,000 separate times, right? That's the whole point of what's going on here. 100 times 20 gets me the 2,000 iterations of the entire loop structure. And notice from a formatting standpoint, this is how assembly language works, is that I do not go ahead and doubly nest the formatting. That's just how it goes. Even though it's doubly nested, the code is only nested one time. The rules generally are that the labels go on their own line, and the labels are basically formatted as far left. They're not tabbed over, or if they're tabbed over, the code is always tabbed over one more than what the labels are showing. So tying everything together a little bit from this, a little bit from previous lectures, and so forth and so on. How could we? There are many ways to do this, but how could we use the advantages of the things we're learning right now to reverse the characters of a string? And in this case, replacing them moving them and changing them and reversing them in order inside of the string itself. So what we could do then is go individually through and push all the characters onto the stack, and then just go ahead and pop them back, because if I'm pushing, the last character that gets pushed would be the question mark. And then we can start back at the start again and then go, okay, let's put it back. So it's a two-step process to make this work. We have to push things onto the stack, and then the second step on the next slide will be to pop them back. And so we have to make sure to keep the null terminating character at the end of the string, obviously, right? Because if I go ahead and I do all the hard work and I leave the 0 and I push the 0 onto the stack, that'll be the first thing that goes in, and the null terminating character will be the first character in the string. And so when I go to print it later, as much as after the 0, everything will be there and everything will be reversed, it'll never print anything because the null terminating character is the end-all be-all to everything. So I have to make sure that I print everything but that final 0. So let's take a look here. So let's push the characters onto the stack. So okay, so I move 0 into ESI, okay, because I'm going to start using array notations for these kind of things. You can see that here. And how many times am I going to do this? I'm going to go, hey, length of S. Remember that one from a previous lecture. So to figure out, what is that, 6, 7, 12, 13? 13 or 14 or whatever it is. And notice right after I decrement ECX to make sure I don't push the 0 onto the stack. That's the big deal here. And again, ASCII characters are 8 bits of storage, so now when I actually go ahead and try to push stuff onto the stack, I have to expand out and actually waste a lot of space to get this to work. So What am I doing? ESI is 0. This, think of this as an array notation like you know any other language, and say, okay, get me S of 0, which is the capital S. Move it, 0 extend it into the entire EAX register. So remember what that does, chapter 3, chapter 4 thing. So this is a character, because this is a byte array. So this gets an 8-bit quantity and expands it out into a 32-bit quantity and just fills in all the extra spaces with 0, because we have to push a 32-bit quantity onto the stack. So that will push capital S onto the stack, increment ESI, so now ESI is 1, and then loop again, and however many, 14, I'll save you the trouble, 14, 15 times or whatever of this, but you can see you do this again. So now go to S sub 1, index 1, which is the lowercase p, and push and move, extend that, and then push that onto the stack. Move ESI over and continue and continue and continue. So what will happen after all of this is done, and since I don't hit the null terminating character, the stack will be filled with all the characters of spring break all the way up to the question mark. So that we understand that much. The pointer, the ESI, is pointing to whatever the, not pointing to, but the value is whatever index value the null terminating character is at, and ECX has been reduced down to 0. So that's what we know, coming out of this loop, because loop changes ECX, we've been changing ESI, and we've been pushing information onto the stack. Notice no discussion here was anything like I was talking earlier about the ESP pointer. This is all just presumed. The pushes and the pops do all of this automatically. I do not have to account for where the ESP pointer is, but I do know that it's pointing to the element that is the question mark at the top of the stack, at the current top. Okay, so popping everything off of the stack now, it's the same kind of idea. Remembering ASCII characters are 1 byte of storage, so same deal. This is the exact same code as before. Set the ESI to 0, because that's where I'm going to be putting the first character from the top of the stack. Length of S is how many times I'm going to do this, -1. Because again, I do not want to worry about that. Well, at this point, there is no 0 on this stack at all. And if I forget this and I do one more, well, who knows what that final character is going to be. And it's actually going to blow out the 0 at the end of the string right here, because that 0 is still part of the string. Because we're replacing in place, we're going to be removing or changing the characters up, the question mark, and then the K, and then this and that, and everything forward here. So now, since it's on the stack, the first thing I do as I'm looping is to pop EAX register. Because again, everything is 32 bits. We only care about 8 bits of it, but everything on the stack is 32 bits large. And so I pop off the stack and I place it into the EAX register. I can put it anywhere, but this makes sense. Well, not anywhere. I can't put it into ECX or ESI, or otherwise I will completely blow out and ruin my program. But EAX is fine, and remember now that I have this information from the stack and placed into a register, I can now extract the 8 bits that matter to me, and that's what AL is. And I'm going to move that into S at the 0 position, so the question mark is going to overwrite the capital S in this case. And then I'm going to increment ESI. ESI is going to be 1, and then I loop again, because this is going to happen 14 times or so. Pop EAX, the top of the stack now holds the lowercase k, and put the 8-bit version of that, the actual ASCII character, at S index 1. So the K will go into the P, increment ESI to be 2, and loop again and again and again. So you see where this is going, that the K will go here, and the A, and so forth and so on, until everything has been reversed. And when everything is done, what do we know again? We know that ESI will point to wherever the null terminating character is. We know that ECX will be 0. We know that EAX will be whatever the last character was. And we also know what here? What do we know? I think that's about everything. If I missed something, ESI, EAX, ECX, yeah, whatever. I mean, you guys can figure that out there. If I missed something, let me know about it. Just off the top of my head, I'm not 100%. But now what I can do to prove everything worked out, or you could even do it before and after, is here's the code to print the string out, right? So take the offset of S, move it into EDX at any time, call write string. And now spring break becomes this guy right here. Looks like complete gibberish, and it is because it's just reversed stuff. Okay, so the your turn here is the same but different stuff. So we haven't prompted the user. We haven't been using the Irvine library too much lately, so let's take a look at this. Prompt the user 5 times for a 32-bit signed integer value, otherwise known as just a plain old int in C++, and then output the values in reverse order. And what's cool about using the stack, as long as you pay attention to how you're doing this, is since it's 5 values, I'm using this push and pop operations for it. I don't have to maintain an array. I don't have to maintain 5 separate registers. I don't have to, I don't have to have 5 separate variables. I can just push and pop, and everything's going to work out just fine. So let's see where we're at here. There's a lot of code here, but you get the point. I put it all on one slide for you this time. And so here is the string to print, enter a value. And so 5 times over, 5 into ECX, loop again with an again label here. Do the 2 lines of code to print the string, enter a value. Notice I put a little space there, so the little cursor will blink right there, waiting for you to read int. And it's a 32-bit quantity coming in to the EAX register. When I hit enter, it goes right in, and I could push it right on the stack. So I said a lot of these things seem very complicated, and they feel very complicated, but at the end of the day, sometimes like this, it turns out to be not a lot of code, especially if the Irvine library is doing that heavy lifting for us. So 5 times over, read int and push it, push it, push it, push it, push it. And so when we fall through, there's 5 pieces of information on the stack, and we're ready to read it in reverse order. And say there's no variables have been used other than EDX, and I need to use EAX, and all this stuff because of the way the Irvine library works. But 5 times over with my loop, pop EAX, and then you obviously want to use EAX because I need that to use for the write int function, so I don't have to do any extra work. So push, pop the information into the EAX register, call write int, and loop again. That's the whole program. Sometimes it takes 20, 30 lines of code to do, something that feels like it should be simple, and this time it's kind of the opposite. It feels like it should be a really complicated program, but it turns out it's not so bad. So let's see what else is going on here. Okay, so push FD and pop FD, and so now you say we can start pushing. We can, so if we can push registers and we can push this, we can actually start pushing flags as well. And luckily for us, we don't worry about this too much. We will see in this chapter and later on that our contract, especially when we set up a function, is that we have to make sure we put everything back to how it was before we finish up. So like basically, however the workspace was when we walk into the room is how we have to leave it, because if everybody's sharing these registers, and if I go in and presuming that someone else was using the space, and I go and ruin everything, well, and I go back and someone else comes in and sees everything's ruined, they won't notice it's ruined, but the program, like in this case, in the way the analogy works, the program will just stop working properly. There'll be a runtime error because you've blown out registers that you weren't supposed to do. And so like this here, things like this, push AD, pop AD, notice you push everything up front. I'm sorry, push FD. That's a little typo, but you get the point here. You push and pop everything. You push before you do anything, and you pop after you've done everything, because the status flags and all this stuff, it's all it's like putting everything back. And so again, we generally don't worry about the status flags. We can, but we're generally more interested in the way that the registers have been affected. And so push AD, we don't see this very often either. I just want to describe it to you. And the reason we generally don't see this is because we will learn in a future slide and future videos that the EAX register is usually blown out and is used for the return value. So whatever function, if it returns an int or a float or who knows what, it's almost always, at least in C++ anyway, it's always the EAX register that is modified. And so what would happen here is if I do push AD, and I do my work, and I set up EAX to return, and then I do a pop AD, as you see here, the EAX register would be put back to how it was. So all my hard work would be for nothing. And so very rarely do we use something like this, and like push AD, which essentially pushes every register on the stack. Right, whatever the current status of every single register on the CPU gets pushed down to the stack. So it's a 32-byte operation because there's 8 registers and 4 bytes apiece. And for whatever reason, it's all legacy at this point. The EAX register is put first, then ECX, EDX, EBX, ESP, EBP, ESI, EDI. It's just the way it goes. And so again, remember, when we pop back, we got to make sure we pop them back, or the system does it automatically, but we got to pop it back in reverse order. And so there you go. Notice that everything is reversed. EDI, then ESI, then EBP, then ESP, then B, then D, then C, then A. And so, what would happen if you forget to push before you pop, right? Like, oh shoot, that's a huge problem, right? You could stack overflow one way, but how often do you accidentally pop and go further the other way? You cannot pop an empty stack. And you usually crash the computer that way because now you're moving out of the stack segment and now you're moving into who knows where. Code segment, data segment, could be just you're out of your walled garden where your program's memory is located. Who knows? All bets are off. And so just a quick little thing here I just wanted to show here, proving that the push AD operation does exactly the way I was describing it. So, and again, we can't prove this exactly for ESP and EBP because, of course, if we blow those things out, we change these pieces of information, then we're blowing out the call stack. And we do not want to blow out the call stack when we're using the call stack to try to prove things about the call stack. So it's this weird little loop. But all the other 6 registers I can prove to you. So like I'm going to use push AD in the next slide to put everything on the stack. But instead of using pop AD, I'll use individual pop operations to display and show you what's going on. And yes, the results will match the expectations. So so again, at a low level, by doing push AD, I'm just putting 32 bytes of storage into my stack. And so there's nothing stopping me from taking them off 4 at a time. There's no rule that says for every push AD I have to have a pop AD. But generally speaking, it makes sense because if I'm going to automate the push process, I should automate the pop process. So here we go. This is just to put values in, and again, you can just put your code individually, copy this and put this into Visual Studio if you want. And so I would put a 1, a 2, a 3, just so I have different values stored inside of here for all the 6 different registers before I push them, so that now and then print out everything prior to. Or is this afterwards? Oh no, sorry. This is the first part of pushing everything onto the stack. And then notice, so this is with the push AD, and I'm not using pop AD, but here I am popping in everything into EAX register because I'm using it to write. So I'm like, okay, pop the EAX, which will print the 6, which is the EDI value, which is this guy. And then I pop again, and now it'll give me the 5. And then again, I can't test this out, EBP and ESP, because I can't really prove anything, but I still have to pop that information off because it's been pushed on, right? Even though we don't see it here, it's been pushed on with the push AD. And then now we're ready to continue, and then, like I said, push it in EBX, EDX, ECX, EAX, that order. They come off in the reverse order. And so it'll print 6, 5, 4, 3, 2, 1, and it proves exactly what we're saying about the order of operations. And again, what does it matter? It doesn't necessarily matter for much, but it's pretty good practice to kind of think the way pushes and pops work and kind of work on a program that maybe you haven't seen yet before, or if you're watching this video, hopefully not for the 3rd or 4th time, you've already seen this 3 or 4 times. Hopefully it's clicking for you what is going on here with the pushes and the pops. The last major topic of this lecture today, since we've already been using the Irvine library. Oh, look at that. Oh, I got green on this. Oh, shoot. Anyway, so creating functions, creating our own custom functions just like you would in any other language, right? We have inputs, we have outputs, or generally one output. Well, sometimes we have multiples. We usually put that into a structure of some sort. but you better know, you should know exactly what I'm talking about how to call functions, how to use functions, and so forth and so on. This is a senior level course for us here at the College of DuPage, so you should know exactly that. So large problems should be broken down into smaller, more manageable tasks. That is top-down design. That is just everything. That is everything about just designing. It's not even computer science. It's just any field, any project, anything you have to do starts as one major idea. Let's make Fallout 5. And from there, millions of little things come up that turn that one thought into a final product. And so you have to watch out, right? Because if you screw up along the way, hopefully you screw up early so you can fix it before it becomes a huge problem. And so no matter what the language, I want you guys to document and comment your code. It's an absolute must. It really is. You might not see it while I'm doing stuff for you here, when I'm doing things like in the lecture videos, but when I'm writing my own code, I'm absolutely doing that, because when I come back to this, I need to know what the heck I was thinking. And that applies across the board. Just because I'm using C++, I come back, I work on something for a few days, and I get busy. I come back 2 weeks later, like, why did I even bother? Because I don't remember anything I did. And if without comments, I'm out of luck. It might as well just rewrite the code, if it, because the amount of time it will take me to figure out what I did, I could just redo whatever it is I was doing before. So just, so obviously you should tell people what your code does, especially things that are tricky. Like, I don't want you to see increment x and then go x, plus x. We get that. It's all, comments are generally for things where you go out of the ordinary and you leave a big note that says, this is why I'm doing things, like duh, like I was really working hard on this and I can't figure this out. Maybe if I can come back, I'll fix it later, but this is why it's the way it is now. So for function names, give me a name that works, right? It's just like variable names should be like, descriptive and describe what they're trying to do. Same with function names. You look at any library for any, for any programming language, the functions aren't called A, B, C, D, and E, right? There's absolute value and cosine, and you name the others. And because if it was just random names for things, nobody would remember all the different details. But I can remember absolute value. I can remember cosine. I can remember this. I can remember that. So this is the general syntax here. Notice it's proc and np. All of this goes in the code segment. It does not go inside main. It's its own separate thing, right? You do not put functions inside other functions. And so it's proc for procedure and np for end procedure. And notice there's a ret here. Don't forget this. So this is how you could start, and then the name, whatever the name of the procedure is going to be. Your code's going to go here, and then you're going to need a ret. This is not an exit. I'm sure there's another slide here that describes that. Main has an exit, but any other function has a ret. So here's a combination, commenting. Think of APIs, right? Just think, if there was no documentation for the programming language, if you just opened up Python or you opened up C++, and well, C++ is a terrible example because it's a terrible language. I love it, but it's a terrible language when it comes to just how much things you have to know, how many things you have to know to get things going. But saying here, what do I have to, if there's no interface, if there's no UI, there's no documentation for it, how am I supposed to know what these functions do? How do I know what to tell it? What do I have to tell it to have it do its job? What does it even return? What does it even do? So comments like this, it doesn't have to, the inputs, returns, notes, things you have to worry about. So what does your function do? This one calculates the sum of 3 integers. What are the registers? So we can say we're gonna change this up in chapter 8, but for right now, what registers do I have to do I have to set up so that this function can do its job? Or what, if it's not a register, what do I have to work with to make this thing put all the givens in the right place so it can do its job? So in this case, I need EAX, EBX, and ECX to hold the integers that I'm going to add together. And the return of this, because you never write a function to print and then not return anything. It's a useless function at that point, unless the function's name is print the sum of 3 numbers, because I can't do anything with that result. I add the 3 things together, I print it out. Well, okay, what if I need to get an average from that number? There's no way for this thing to return back. So the EAX register, as you see here, is where the sum is going to go, and that's what's going to be returned back. So the presumption is EAX is going to be modified, EBX and ECX is not. And then let's see, the status flags are modified by this function, which is a given because it's add functions and whatnot. And so again, garbage in, garbage out. And so you actually, in this case, you could return multiple values in assembly language because you're just tinkering with registers. But again, to keep consistent with every modern programming language, you generally don't do that. You would set up, like if Python, you'd set up a tuple or something like that, or C++, you'd have a pointer to a structure or a class or something like that. You say, even in Python, when you think, oh, I'm returning 13 things, it's like you're still returning a collection of 13 items. It's still returning one pointer to or one reference to a collection of information. Okay, so how to use these functions on the other end. If this is the function that sets everything up and is the sum of function, how do I do this? And we already know this since we've been using the Irvine library. We use the call operation. And so no big deal there. So we say call sum of, but we have to make sure we set up all the registers before we do the call, of course, right? Basically like pushing the parameters into the function when we call them in C++ or Python or you name it, it's the same kind of deal. And so what happens is, this is all the technical stuff that happens under the hood. The offset of the next instruction that is performed once the function returns is pushed onto the stack. So a memory address, when I hit call, is actually thrown onto the stack because when this function ends, how would the program know where to go back to? It's just magic, right? The program just somehow knows, right? No, that information is stored. So when I hit return, it goes back to wherever the call was and goes, oh, here's the next line of code. Let's go there. And let's see. And then the memory address, when that is done, when I push that information onto the stack, so it's like a two-step process, right? To call a function, I put the memory address on the stack, and then the instruction pointer goes to the function. So wherever from the call, put your little finger on the add. Where is it? That. Put it on there. That's the line of code it's now running with everything. It's as if nothing ever happened. The instruction pointer is now looking at this line of code. The registers are hopefully set up the way they're supposed to, and now you're ready to go to town. So that's what the slide's trying to represent here. So the ret operation is, say, the main function uses exit. Exit is like your return 0 from main or your exit function in C++. I don't know if Java has just a complete abort or something like that. Sorry, it's been a while for my Java. But the exit is completely different. Exit tells the operating system, we're done. Go back and this program has terminated. But the return says that I'm done with this specific function. And so that's what this is saying here. The ret, you use ret, and make sure you have, I guess it's worse to have nothing than it is to have exit, I guess. Because as we'll see, because actually the program will keep on going, it'll fall through. It's not like C++ where it hits that closing curly brace and it just automatically nicely returns for us. If we forget this, huge problems occur. And so when we hit return, when we hit that return statement, that ret, as you see here, what happens, as you can imagine then, is the unwinding of the previous operations is the top of the, whatever's at the top of the stack at that current moment in time is popped off, and that value is directly put back into the EIP register because that was the memory address of the next line of code in the original function that made the call to the other function. And then, let's say once the function has officially returned, with the EIP register now holding the next line of code to run, it's time to move on. And now we're back in, and we're back, whoever called this function, now we're back in, and now we can process the EAX register is holding the correct value, and if I need to print it or whatever I need to do, I can go ahead and do that. So here is a little more detailed example of this. So let's say that 00025 is the memory address of the instruction immediately following the call. So I want to call fun for function, and it's at 20 hex, and it's it's 5 bytes to do this, 1 byte for the call, 4 bytes for the memory address. And so what happens is, when I do the call with everything else that's already on, everything got pushed onto or everything's going to get pushed onto the stack. The 25 here is going to get pushed onto the stack. ESP is going to point there, and then see how this is worked out. That was part 1, right? Move the information onto the stack, so that's where we return back to the line of code after the call, and then push the instruction pointer to the actual function. This at 40 hex is where function begins. This line of code. And so now the instruction pointer, and they're like, okay, let's just run this line of code like it's nothing. And then blah, blah, blah. It's only a one-liner. Let's just do one thing. And I return. And when the ret happens, whatever's the top of the stack gets put back into the EIP. This thing is popped off, so the stack is empty after this is done. And then we're ready to move on. We're ready to move to line 25. Function is complete. I'm back to where it was called from. I'm ready to do the next line of code. And so it's pretty cool. So it all works out. Again, pretty much everything is like it's using a stack. So everything is a stack. I'm pushing information. I'm popping everything off. And as long as for every push, there's a pop, and it's all in the reverse orders of each other, everything's just going to work out. It feels like magic. It's really cool. I think it's nerdy computer cool stuff here. And when it all just comes together, when all these complicated functions are calling one another, and it all just falls in line. I think it's amazing how it works. Obviously, we could nest function calls together here, right? Because that's what reality is. This function calls that function. In the middle of this function calls another. That calls another. This loops inside here, calls this, and comes back. And it's saying everything just winds and unwinds just naturally. And especially when we get to chapter 8 with all the way that the local variables and the parameters actually get passed, this stack is just like ebbing and flowing nonstop. But we're not there just yet. But just to say something like this, if I have a function, I'm in main, I call function, which calls, typo, function, let's just say fun1. Fun1 calls here, which calls fun2, which calls fun3, with boom, boom, boom. It's like, of course, what happens? The stack is maintaining the information, again, of where to return to when any specific function call, whenever, we call it, what do they call it? Activation record. And when basically, what is the status of everything at the current moment in time inside of a current function? And so, as we're saying here, the main, I call fun, the 25 gets thrown onto the stack. And the instruction pointer goes to 40, which was where fun is. And when I say, let's call fun 2, well, 46 gets thrown on the stack because that's where I'm going to return back to when I get done with this. And then I move the instruction pointer to 54. And then now again, I call fun 3. I go, let's push 58 onto the stack. And then move the instruction pointer to 62. So that's where we're at right now, the whole stack operation. And then when this hits return, what happens? This pops off, the 58 goes in here, so I'm going back to here, which is a ret, and so the 46 comes off the stack, gets put into the instruction pointer. I get to here, this is a return, and so now the 25 gets thrown on the stack, thrown off the stack into the instruction pointer, and I'm put back here, and now the program exits. And again, notice these are returns, but this is an exit. My program is completed. And the stack has been emptied, the instruction pointer's in the right place, and we have no worries and no bother. Everything is going to work out just fine. And again, if all you have to do is mismatch one push and one pop, and this is going to crash to holy heck, because when you're dealing with this kind of stuff, when I'm at the top of the stack, and if I'm not getting a memory address of something I'm supposed to be getting, I'm getting it like 3, like a value. Yeah, you're never going to be able to go to memory address 3. That's not going to work for you. So you have to really, really watch out with your pushes and pops as you're doing all this kind of stuff. We showed earlier about function parameters. The way we're doing things now is not the true best practice way, but no matter what, we should always try to make our functions flexible and more general. This happens a lot between students. They all, like, why my function works perfectly. Why did I get points off? And it's because you are not supposed to be using global variables ever inside of a function. That's just not how things work. You're not supposed, other than the fact that assembly language, at least for now, needs to use global variables, no other language does, right? In a modern world, we avoid global variables, maybe Python, but is it truly global or whatnot, the way the whole namespace gets set up. But just think in C++, we no longer, in Java especially, there's no such thing as global anything. Everything is object oriented. So it's just not a way that we go ahead and do things anymore. So we want to make things flexible, and the more flexible, the more generic we can make our functions, the more they can be reused. Can you imagine if you had to know so many details of like an absolute value, or using an array to pass an array in, and like for specific functions or whatnot? No, this takes experience, this takes practice. This is not something that comes to you immediately. You try things out and you learn from the mistakes that you've made. Again, this is something that just takes time. And using specific variables when you're hard coding. If I have to use a specific variable, I have to use a specific array. Well, what if I wanted to use a 10-element array versus a 6-element array? Sorry, it's not going to work for you. No, that's not acceptable. It's not acceptable in C and Java. It's not acceptable here in assembly language as well. So we have to think ahead, and we're going to make things flexible, since all of the parameters should be changeable at runtime, just like we can do in any other language. So here we go. Here's a poor example. Again, it works, but what are we doing here? Array sum function calculates the sum of an array. So here's my array. Here is my hard-coded sum. Here is the function that will do it. And so, it's a double word. Everything's double word, double word, double word. And so, why am I even using sum? Yep, I'm using sum here at the end. So, yep, instead of passing and returning the EAX register, I'm returning it in sum. So that means that right now that's screaming out poor design. It's using that global variable. It's using the global variable sum. It's using the global array. So everything else, it will work. It'll go through ESI is 0, the accumulator is 0. Do this however big array is, do this 5 times over. Go get the element, put it into EAX, add it in, move 4 bytes over, do it again. So EAX will hold 15, put it into sum, call it a day, return back. But how can we make this more generic? Sometimes it takes more code, obviously speaking, and sometimes, like anything else, sometimes it's actually easier, sometimes it's harder. In this case, it's, but when we do this way, we're actually shifting the burdens of setting up and using the function into, the main side and the function side. So how many lines? This is actually 10 lines of code. This before was 8 lines of code. So it's a little bit more code, but again, now it's a little more flexible. So what do? I have inputs. Instead of hard-coded arrays and values, the ESI pointer is pointing to an array of double words. So ESI is all, when this function starts up, you have to supply me ESI, and then you also have to supply me ECX, which is the size of the array. So what happens down here is when I have array, it's in main, I can get access to array from here, but when I pass a general pointer, I lose all the other information from it. I can no longer get the size from a general pointer. I could from a global variable, but I can't from just a general pointer. So I have to pass this information along. Here's the offset, here's the pointer to my array, here's how many elements I want you to add together, and then go do the work for me. And so EAX starts out as 0. Okay, fine. So we're doing this the hard-coded, or the direct pointer method way. We're not doing things the old, like the more standard professional, or the way more programmers understand arrays, with the array sub-bracket notation, a index 0 or something like that. Just go give me ESI, dereference it, add it into EAX, move over 4 bytes, do it again, and just keep on going however many elements I have to, and when I fall through, the EAX register holds the result, and that's what gets returned. And so I can immediately call writeInt, and notice now if I wanted to maintain that in the thing called sum, like before it was directly put in there, at the end of this function, now that goes here after I return back from the function, because EAX register is the go-to register for return time. Here is my entire program working in Visual Studio now. I just basically just copy-pasted everything over. And you can see for this array 1, 2, 3, 4, 5, it comes out as 15. And so offset and length of are done in the main, call, write, return, do all this stuff. And so what's cool about this, again, by making everything more flexible, if I just add 6 and 7 here, everything works for free. I don't have to do any more work because offset, pointer, length of is done automatically at assemble time. I don't have to come back and turn ECX into a 7 or a 6 or 5, but whatever the number of elements are. It's already done for me. And so the sum is moved in here. 28 is in the sum. Perfect. It works perfectly fine. So one other thing I wanted to describe here, which I guess I don't have in this slide set, it's very important as we're discussing. There is a such thing as returning your workspace back to whatever was going on. So in this case, what I have to do is, and so I have my function working. That's like the first thing you should ever worry about, is just getting the thing working at all. And then so now I'm very confident, I'm very happy about this. But what happens here is ESI and ECX have been modified. So what if so when the function returns from array sum, ECX and ESI have been completely ruined. And that's not good, because my contract was to only change EAX, which I did, because it returns everything right. But everything else needs to be put back to how it was. So this is what you do when you say that if you get things working like this, and then so you have it working perfectly fine, and what you do then is you go through and you go through and you're like, what have I modified? One way to do this is to call dump regs before and call dump regs right after. If you could go through and look to see what's been modified, but this actually kind of helps you with things. And what I can see here is that, yes, the EAX register has been manipulated, but that is a guarantee. Let's see, but EBX has not, ECX has been, right? 7 has become a 0. EDX has not changed. ESI, yes, ESI has changed. EDI has not, and I don't have to ever worry about EBP, ESP, because that is part of, even though they are the same here, those things are maintained by the push pops and the calls and the rets. So I don't have to worry about that. But I do notice that those two registers, ESI and ECX, have been modified. So what I do is I have to push, and it doesn't really matter what order, at least up top. But when I come back down here, I have to, but right before the return, the last thing I do before the return is pop everything back in the reverse order. So push ESI is the top, pop ESI gets the top back. So again, so now everything looks better than, it works better because only EAX is modified when I come back from this function, and I can reuse ECX and ESI. And so yes, sometimes you'll have 3 or 4 of these pushes and pops on either end, and sometimes your push pop code is half of the real code, but that's the reality. These functions need to do these things and promise that they only modify certain values and put everything back to how it is. So just to reiterate with the slide in place now, that you push all the registers that get used in your function that are not part of the return values. So I said we have a contract to put everything back how we found it. That we if you just go in here and I guess it's irresponsible just to go in and just say I'm ruining everything. That's the lazy approach, right? The professional approach is to make sure that you put everything back except for, in this case, EAX. And so notice here, like what would happen here if I did a push EAX and a pop EAX, right? Going back to the original function, did I already pass it up? No, here it is. The original function added, and returned. And you're like, okay, and so it works. But what if I did, whatever I just showed you here, and I go, okay, I push and I pop. let's say, but what happens here, all the hard work, because the EAX register is what I was supposed to return. And I did all the hard work here with the two adds, like I showed just a second ago. But if I push and pop, that value is blown out and the EAX register is returned to whatever it was prior to the call. And by doing that, I basically didn't do anything at all, because the EAX register is the only thing that's modified, and by putting it back, it's useless, because there's no value. I'm not going to get back the value that is the sum of the three values. So you have to make sure basically EAX is off limits. The only time it is on limits, or there is a chance to push and pop it, is when you basically have a void function, a function that does not return anything. Then EAX is part of the game. But otherwise, you never push pop EAX, but you push pop everything else you use. And sometimes it's tricky. Like looking at this loop again, the loop indirectly plays with ECX. And that's why I use the call dump regs, because it's very easy to forget something like that, even if you're experienced. And when you get to multiplication and division, where EAX and EDX are used anytime you do anything like that with multiplication and division, it's very easy to forget. So if you do the call dump regs at the end there, fix everything up, you're pretty much good to go. Okay, so I think that's a good example there. Last little thing here. So I say we're using the Irvine library, we're writing our own code. Eventually you could write your own libraries. That's somewhere, I think it's like chapter 12 or 13 in here. You can actually compile down your own code. You can actually create your own assembly language functions that tie directly into C code. You could write C code that uses these functions in your own libraries. I think that's really cool. But the link library, the Irvine library, is essentially a file that contains all the functions that, in that case, that the Irvine library has created for us. And they've already been assembled down into machine code. And so the ways I'm showing you now, all the things we're doing matter, because there's a certain procedure and protocol to setting everything up so I can use this in C++ and so forth and so on. Every language has a protocol on how functions get set up. And so if I ever did want to put this into a library that I can use elsewhere, a really tight, efficient, compact library, well, I have to follow the rules. And also then I can have multiple files. Again, we're never going to do more than one file in this whole course. But if you ever needed to, you need a way to kind of make them all work together. And so you would create an empty library file, a lib extension, we get OBJs. I've never actually gone into this, at least with assembly language. I've set up libraries in other languages and things like that, but I've never done things here. But just so you know it exists, if you ever wanted to go ahead and go further into this now that you know how your own, the functions work. Since we don't have object-oriented programming, we have access to structures, but not object-oriented programming per se, that the functional programming is as complex as assembly language can get. So you can't create an object. You could simulate and write your own code for object-oriented programming, but there's nothing inherent in the language itself that can make this work. Okay, that is it. This video is complete. So as always, swardb@cod.edu is a great way to hold of me. If you have any questions, send a comment. The only comments I get are bot comments, so whatever, it's all good. So yes, the one thing you never do, sit on your questions, send me that question. Don't let this snowball. We're pushing into the big stuff now. Functions are basically the final exam is setting up functions, and more setting up functions. So you gotta get this in, get this into practice very soon. And I'm here to help. Please let me know if I can. Thanks for sticking with it, and I'll see you next time.